next lecture in the Spotlight Stay at Home series. Keeping up with our aim of inspiring, energizing, and helping the student community, we have with us today Mr. Rajat Monga. Mr. Rajat Monga is the co-founder and former lead of TensorFlow at the Google Brain team that powers machine learning research and products worldwide. As a founding member of the team, he was involved in co-designing and co-implementing DistBelief and more recently TensorFlow. Prior to this role, he led teams in AdWords, co-designed web-scale crawling and content matching infrastructure at Attributor, and co-implemented and scaled eBay's search engine. He received a BTech in electrical engineering from the Indian Institute of Technology, Delhi. Rajat left Google recently to bring machine learning to some core areas in the business world. We are delighted to have you with us, sir.
Thank you. It's a pleasure to be here.
So we shall begin our fireside chat session now. We have prepared a few questions for you. Starting off with a general overview of artificial intelligence. Today's artificial intelligence includes successfully understanding human speech, competing at the highest level in strategic games such as chess and Go, autonomously operating cars, online assistants, and military simulations. Where do you see the scope of artificial intelligence expanding?
So it's great to see all the progress we've made over the last few years, and that's exciting. I think there's still a long way to go in terms of where we are headed. So some areas that are exciting from a pure technology perspective are things like unsupervised learning and more advances in reinforcement learning and so on. From the user perspective, I would say robotics is one big area that's seeing a resurgence and really lots of growth and improvement. The most common case for that, of course, is the self-driving cars. But there's a lot more to robotics than just that. And even there's still a fair bit of work to be done to get it to the kind of quality we expect for us to use in day-to-day lives. I'm sure we would all love a robot in our homes helping us with all the work that we have to do. So really looking forward to that.
Right. So you mentioned about autonomous cars, robots, and we also have systems like DeepMind's AlphaGo and IBM Watson coming up. So do you think we are slowly progressing towards artificial general intelligence?
Yeah, AGI or artificial general intelligence is something we all would love to have in some ways, although there are some scary aspects of that too. That said, personally, I believe there are still a number of things that we need to achieve for us to get there. So it's still a fair bit away. I don't think we are going to see this in this decade. It's probably beyond that. There are, the last progress in some ways we've made based on, how much improvements in technology we've seen and how, different kinds of things we've done, both from the algorithmic side and the hardware side. I think with where we are leveraging a lot of that hardware now, and in some ways, pushing the limits of where we are. We probably need a few more bumps on that. Maybe, as I like to say, a few more 10x improvements. Maybe, if we had 1000x more compute today, we could probably still use that and not quite be there yet.
You mentioned the development of hardware helping us, but the technology is also developing, as in the software. A recent study shows that AI is developing on par, if not faster than the hardware, and doubling in power every 16 months. Do you think there might be a stage where our hardware will be incapable of handling the software?
In some ways, yes. I mean, in some ways, just going back a little bit, if you think about the core neural networks, this concept has been there for 50, 60 years now. It took us a while, primarily because of the limitations of the hardware. And there were other improvements as well in terms of the backpropagation and some of the other techniques that really helped the algorithms. But even beyond that, the hardware made a big difference. Both of these really had to come together for it to work well. So as we've scaled up, I mean, we've seen from, say, even a decade ago, or 2011 or so, when I got into this field, the hardware that we had then, where we were using tens of thousands of CPU cores with very much smaller, simpler CPU cores, to today, where probably a single GPU system or a TPU box has way more power than that, and we can have hundreds of those together or so on. Even with this, though, we see, in terms of experimentation and pushing the boundaries forward, we are usually still limited by where we can go with hardware. There are things, yes, we can do from the software perspective to leverage that hardware better, I would say. But I think some of these go in, um, in some ways, the last decade has been this golden age where we've had both the software and hardware making improvements together in an amazing way, which has led to these great improvements. Often it's one or the other. And that, in the short term feels like, okay, we've hit a brick wall. But I think that also leads to a lot more interesting innovation in different ways. So, for example, going from CPUs to GPUs was sort of one innovation where you could leverage a different kind of hardware. That was interesting. But this also led to completely new kinds of hardware like TPUs, which have, in fact, eventually made, some of those ideas have made their way back to GPUs themselves, like matrix multiply units and optimizations and so on, that are really, really exciting. And so, yes, it's possible in that sense that the algorithms will start to push us on the limits of hardware, and that's going to be the primary bottleneck in the next few years. My guess is it'll slow things down for a little while until we figure out the next big change in this from the algorithms perspective to take advantage of this.
You mentioned scaling up and wide use of algorithms. So in that sense, data is the new age oil. Data is involved in our lives every day, right from our smartphones to our PCs. So given the rate at which technology develops nowadays, do you think we are moving towards a largely data-driven society?
In some ways, yes. In other ways, no. I would say yes, because a lot of these algorithms, like we're talking about, yes, totally, like you said, they are data driven. They improve with more data that they can get. And so, if you look at how many of the big companies learn and leverage things like ML to deliver value, it's from data. In some ways, if you think about even, how you think of large marketplaces like, say, Uber or Airbnb and things like that, they're, in some ways, the value that they're providing is the data that connects all these together and really leveraging the data to provide better things. So in that sense, yes, data is very, very powerful. In other ways, though, we are looking at, from an algorithmic perspective, there's more push towards being able to do the same thing with less data for a number of good reasons. Compute is one place where we are limited by the compute. Another is where we can leverage, techniques like transfer learning to go from, okay, we already have a trained model. Can we, just train with just bits of data to customize it for the specific case? Why do you need to train everything from scratch? That's just expensive and so on. So it's going to be a mix of things. That said, data is going to be really, really relevant from both, what you can do and where you can push this technology and research, but also from a business perspective. Businesses do want to be more and more data driven. Combining that with algorithms is going to be really interesting for them.
Right. With respect to ML used to leverage all this data, big data is used in a lot of fields right now, right from IT industries to biomedical purposes. Collecting large amounts of data and using it effectively can be quite troublesome. How does machine learning advances help upon that efficiency, and how widely are they used?
Yeah, it's interesting. The whole idea of collecting data, organizing it, etc., there's been a lot of work in this area that's happened for a long time, right? And the data is continuing to grow. Machine learning, in some ways, is building on top of a lot of that infrastructure that was there. But that said, it's also pushing. It's one of those areas that really leverages data well, and so it's that one application that you end up optimizing a lot of the data platforms for. Now, in turn, of course, we're starting to see areas in infrastructure management and software for infrastructure where we're starting to apply machine learning to improve that software itself and the infrastructure itself. And so that's a great cycle, to build upon itself and really make things better. That said, specifically from a machine learning perspective, the good thing is that the data access often is, there's a lot of data to access, but it's also simpler. It's not the same as, say, accessing a database where you're making random accesses across the board. You want to go through the entire data, maybe more than once, maybe once, etc. At least while training. And then, of course, while inference is just no different than any other function call in some sense. And so it's led to different kinds of optimizations that are really focused on areas that make it easy to build these models and really learn these models on top of what kind of data you have. So certain kinds of optimizations that we'll continue to see. The whole idea of big data where you don't necessarily need all of that in the database, and you have on the open source side things like Hadoop, etc. That has changed things. That said, with this, I think we are starting to see a whole new layer of abstractions that are working well and optimized well. For example, on Google Cloud, I believe accessing data from, say, the GCS or BigQuery both end up being fast. In fact, BigQuery is often faster, even though it's a more structured data, just because of how it's layered and how it's distributed, how well it's distributed across machines.
Talking about ML used to optimize the software, can you give examples of products of how products have been optimized by ML by big companies like Google, which primarily focus on software?
Yeah, so that's a great question in some ways, but we've looked at all the layers. What I was referring to was more at the infrastructure layer, where I would say there's some early explorations in some places where we've actually done optimizations. For example, we had a paper on, I think about a year or two ago now, in terms of leveraging machine learning to optimize or pick the right cache sizes or cache coherency, or what to keep and what to throw out, etc. So some ideas there. Also looking at some of these to optimize some of the broader, different kinds of hyperparameters that you might use for, which people usually just pick a heuristic for. So at the infrastructure layer, there are ideas like that. But as you go through the product, there are all kinds of different layers. So for example, a product like search, which everybody uses, of course, that's being improved upon by the core models in search itself, right? That's just a core change to the product. Machine learning in some ways is a key part of that product today, and it's a huge signal. Some of that, it's a combination of lots of signals. This is probably one of the most important ones today. There are other products like, say, Google Photos, where again a key feature is driven by this, where the recognition of the photos, where you can search by a person or cataloging and all of that is completely driven by this, right? And in some ways, that product was built from the ground up to leverage this, because it was built at a time where this was starting to come of age. There are other areas like, again, translate. It really wouldn't work without machine learning. We leverage machine learning as pretty much every part of the stack to understand the language, to do the translation. If you want to see it, scan or do an OCR, again, there's machine learning there. So again, depends on the product. Different parts of the stack use machine learning, and I would say pretty much every product that I can think of at Google uses machine learning in some form or another.
That was great. So you mentioned about neural networks existing over the past 50 years. Though computational models of neural networks have been around since the 1940s, they had not been predominantly used until research in AI was carried out. That is the late 1990s to the early 2000s. How do you think deep learning has evolved over the years? Because deep learning employs artificial neural networks.
Yes, I mean, it's I would say in the simplest way, it's a rebranding of artificial neural networks. The term sort of went away for a while and then came back. In fact, in the 90s, when I was doing my BTech, at some point I considered using neural nets for one of my projects to do character recognition or whatever. We ended up not doing that, but it was still too early at that time. That said, I think there have been a number of improvements since then. From the algorithm perspective, training these neural networks has become a lot better because of a few small things sometimes, which added up over time. So, you can train, there are consistent ways that you can train these networks, and that if it's repeatable, you can do it again and again and again. It's not like, a lot of the magic that used to be there, say 20 years ago, in some ways is gone. Anybody can pick up a library off the shelf today and really train their networks, and that works. That really helps. And some of that is due to simple things like, in terms of the nonlinearities, for example, ReLU was great. Again, small thing, but it adds up in terms of how much simpler it's made to train the networks. For example, even in 2011, when we started out, the best way to train it was layer by layer by layer. So you train one layer, then you train the next layer, and so on. today, most people just don't, they just take the entire network and train the entire thing together because, again, this one simple thing. Some of the optimization functions have improved. So going from plain SGD to or stochastic gradient descent to something like a Atom, which is very commonly used, or some of the other even fancier ones. They take a lot of stuff away from the extra things that you have to play with. There are techniques for, and again, this is more recent, hyperparameter optimization that automate a bunch of stuff that you might have to do. Uh, Now, all of these, of course, is in the algorithms layer. The other side of it is in the hardware itself getting better and the tools themselves getting better. And so, from the hardware perspective, just each generation, I mean, until not too long ago, Moore's law was helping from the CPU perspective, and we saw those gains come up. And in fact, all the hardware, even GPUs or TPUs as well. And now, over the last few years, we're seeing the custom accelerators like GPUs and TPUs really starting to help get that extra, again, another 10x, 20x, 100x advantage over what you might see with CPUs. So it's a combination of all these things over time. I think tools have definitely helped in terms of wider adoption. Not necessarily, I mean, research, they do help a bit. You are often, it's, like they say, if all you have is a hammer, then everything looks like a nail. And that's definitely true from a tools perspective. You sort of get limited by what your tools allow. And so that's really helped people do a lot more.
Right. You spoke about the improvement in hardware. So a study shows that from 1991 to 2015, the computational power of hardware has increased around 1,000,000-fold. So this has led to an increase in applications of neural networks and making the algorithms feasible for training networks that are several layers deeper than before. So how do you think an improvement in the hardware is going to affect the deep learning progressing in the near future?
Yeah, I think hardware continues to help. So if you think about there are different parts to it, right? One is, okay, from an application deployment perspective, what do you want? And there are certain kinds of things, certain kinds of improvements in hardware that help making running the inference, actually, that making the predictions cheaper and faster does allow us to deploy more of these in real applications. Even at Google, which has a lot of infrastructure and lots of compute, often deploying these neural networks until we got all these custom chips and stuff was hard. And that's primarily because why Google started to build its own TPUs to deploy all these amazing algorithms that we were building. And so making that faster and cheaper really helps us not worry about that infrastructure cost in terms of deployment. So there's a bigger need for us to build these models and try out new things, right? That really, on the other side, allows us to invest a lot more in research and pushing the boundaries of where we go. And on the research side, compute still ends up being one of the bigger bottlenecks in terms of the progress that we can. That's not the only one. I mean, there's a lot of other things. But if you think about what a single research scientist could do, they have, I don't know, anytime they might have 3 or 4 different ideas that they want to try out. And usually, even for one idea, they can only try out a few experiments at a time because that's as much hardware as they have. If you can do more, then that allows them to do a lot more experimentation. So that's just in terms of exploration. And for even today, we've seen that as we continue to scale the network sizes, with almost no other change, if you have enough data, it ends up getting better. So as simple as that. I mean, as long as you have the data, there's almost no limit to how far you can go with this. And there are places where we don't leverage all the data we have today. That continues to grow, but there are lots of places where we don't leverage it.
Let us talk a little bit about your career now. Before joining as an ML expert in Google, your work in Attributor and eBay led to the overall development of those organizations. What led to such a great success, and how did that experience help you later on?
Yeah, so I've always liked to learn new things, and I've always been excited about exploring new things and pushing the boundaries of things. In each of these organizations, I've been at many companies before that as well. For me, one thing that was always important was A, of course, am I adding value to the organization? And B, am I continuing to learn new things and doing new things, right? Not just sticking it around with exactly what I know. And I think that combination has helped over time. I was in a number of startups before eBay where I learned, I ended up building all kinds of systems because, there were very few engineers in startups. You are basically, each one of you is pulling a lot of weight. So that really allows you to push on different kinds of things. And that experience came in handy at eBay. We were building a search engine. This was, a while back, and some of that infrastructure stuff came in handy. Of course, I learned a lot at eBay as well. The kind of scale that eBay was at that time, it was one of the really big companies from of that age, of the 2000, early 2000s, I guess. Going from there to Attributor, I was able to apply some of that, but also learn some new things again, both in terms of scaling the technology and also in building teams and the organizational pieces and so on. And I would say at Attributor, more than just the technology, I learned about those organizational pieces as well and how to leverage that and how to go beyond. I think in the long run, that's helped me a lot.
You had been part of the Google Brain team right since its inception in 2011. Tell us a bit about the early days of the Google Brain team.
Yeah, those were fun times. There was other than I guess Jeff Dean and Andrew Ng were both there one day a week. Jeff would code up whenever he got time from other projects as well. And there were three of us. We were each working on different parts of the stack or doing some research as well, often, and every day, because it was a very small team, first summer we got two interns from Stanford. In fact, both of them are still there at Google. One went away for a little while and then came back. And we had it was a great experience for me because I did not have any ML experience before that. So all the machine learning I've learned, I started learning then. And these, especially from these two particular interns who came from Stanford, who were doing their PhD in deep learning, they were great teachers in that sense. And so learned a lot from them, worked with them to build out that early infrastructure to explore all these new ideas. We, kind of believed that if we could scale this up well, then we would be able to get some interesting results. We didn't know how far it will go and where this was going. But those early, experiments were good. We had the right set of people to really make some of those differences, make some of those things happen. I think the different backgrounds that each of us had that, allowed us to bring different things to the table, that really helped because we were able to explore lots of different things, come up with, combine a lot of these different ideas and really work together well. So I think that setup, in some ways is really hard to replicate, but that worked really, really well.
Talking about results of the Google Brain team, one of the major breakthroughs that the Google Brain team had was when the cluster of computers learned to recognize a cat based on those 10 million digital images. Tell us a bit more about it.
Yeah, so that was a fun project. One of our interns, Guak, who's been more involved in the auto ML efforts now, he was running these experiments on YouTube data basically, and the idea was, in fact, he was exploring the idea of unsupervised learning, which that was probably one of the biggest experiments ever for unsupervised learning. Even now we haven't really pushed too much in that area. That's still seems like one of the next frontiers. But back then we said, okay, that seems to be a key part. Let's push on that. And the supervised learning was not as good as it is today, or we hadn't really proven that out so well. And so we started collecting a lot of YouTube data. YouTube was one place where we had lots and lots of videos. And the good thing about that is we can just take all these pictures. Because we don't need any labels, we could collect as much as we wanted to. It was limitless effectively. And so we started training these models, or Quark rather started training these models. And in parallel, we were figuring out, okay, we have so much data. How do we get the compute to make this happen? And we tried all sorts of things to really push the boundaries, both in terms of, back then we were looking at data parallelism and model parallelism. In fact, first it was just model parallelism, where we split this one model across I think the maximum we went about to was about 250 machines or so. These were like slow CPU machines, so it would take a long time for us to train that stuff. And we pushed the boundaries of all kinds of things. I mean, both from the infrastructure perspective, and Quark was the primary one driving the algorithmic perspective, and how do we try different kinds of things. Um, and I think that collaboration across a few of us that were working on those ideas really helped push boundaries, and both made the core infrastructure that we were doing, DistBelief, better, of course. But from an algorithmic perspective, that was the first time we could actually, do such an amazing job learning from, these kind of unsupervised images. First time we had scaled it to such a large thing. And it was all done in a space of a few months with just a handful of people in this way.
You mentioned about Geoffrey Hinton and Andrew Ng. You mentioned about working along with them. We had Geoffrey Hinton delivering a video conference in a past edition of Shaastra. Obviously, the team consists of people having a very wide background. Geoffrey himself has a BA in experimental psychology and then a PhD in AI after that. With having people from a wide background and based in different locations, how difficult was it for all the researchers under Google Brain to work towards one common goal?
Yeah, I think we had a very good. I mean, now of course the team's very big and very very distributed. Back then, actually, most of us were in that one office in a small room, basically. So at least that part was good. In fact, Jeffrey Hinton himself, was there 6 months a year or so, when he joined Google. So he spent a lot of time with us as well. And in fact, even when he was not there, we would usually have sort of a screen with him on there pretty much all the time he was in office. So it wasn't, that part wasn't so bad. In terms of pushing towards one idea, I think it was a mix. We always had a small number of ideas where we wanted to explore things, where we thought that were interesting, directions that we thought would be interesting to push towards. For example, even the first year, we had two key things that we were pushing on. One was this image one that we talked about, and one was a speech one, and just making that better. And there we were collaborating with the speech team at Google. Over time, the number of ideas grew, so we always had a few, say a handful of people on each of the ideas and pushing in those directions. And then some folks like myself were looking at, more, I was focused much more on the infrastructure and would occasionally get involved in some of those. And there were others who were in similar boat as well. But overall, I think the good thing about these different experiences was that a lot of these different ideas do come together in a good way. So that's one, we always talk about diversity in different ways. This is another diversity of ideas that really helped us, I think, innovate a lot more back then than you would otherwise. And having everybody from the exact same thing was hard. In fact, this is something that Google Brains continued to try and support and push towards. So, Google Brain has this, or now the broad Google AI program has this residency program, AI residency, where there's a, focus on trying to get people from different backgrounds. Not everybody is a PhD in deep learning or machine learning who comes there. People often have learned parts of that, but starting with different kinds of backgrounds. And that definitely adds value.
So when you were moving in from DistBelief to TensorFlow, that was a time when deep learning was on the rise. So how did you cope up with the changes, and how did you better equip yourself with deep learning?
Yeah, so personally, I started learning deep learning, I guess, that 2011 when I joined this group. Like I was saying, I learned a lot from those two interns, Kwakli and Nyam, and also Andrew Ng. Andrew Ng, actually, the course that he eventually taught externally from Stanford, that was one of the earliest and the largest ML courses. At the same time, he taught that internally as well, and then I just read a lot of papers. The good thing was with the papers and the people around and sort of building this infrastructure, I was forced to learn a lot of these. Back then, if you remember, the tools weren't there when we were building the early tools. There were things like Theano, etc., but for what we were doing, we just couldn't use those. So we had to really write the code. It took me for some basic ideas, even within DistBelief, I remember, just building an autoencoder we did it like 5 different times before we got it to a point which we kind of liked, and then we threw it away and redid it in TensorFlow basically. Because every time we would get one more concept in a better way in some sense, and that allowed us to build better abstractions from the infrastructure, and that, I know personally it helped me a lot. And then, within Google by that time, I would say by the time we were building TensorFlow in 2014, we also had classes for folks across the company, where folks from Google Brain and some other teams who had knowledge of deep learning or had been using it would train other folks as well, because this is starting to be really powerful.
So making TensorFlow open source in 2015 was a very key decision. What led to converting it from proprietary software to open source?
Yeah, that was exciting. So even that whole journey for going from DistBelief to TensorFlow, 2014, we've been doing this for 3 years. DistBelief is starting to get old in the sense, okay, we've made so many iterations of changes that it's not quite keeping up with what we want from it. We wanted a lot more research. We wanted to do more things in production. We knew there were limitations of this. We were starting to use GPUs by then, so we had shoehorned all of that in DistBelief, even things like sequential networks like RNNs or LSTMs. And it was okay, but we were starting to rip out large parts of it and rewrite it. And so, in fact, Jeff came up with the idea, why don't we think about rewriting the whole thing and redoing it? And, that's how the core idea of TensorFlow came out. And in fact, as we sort of started iterating, going in that direction, again, it was Jeff's idea to think about, okay, why don't we think about open sourcing it? And again, this is something that Jeff had seen this history where Google had published a lot of papers over time. And pretty much every system that Google built, eventually Google would publish a paper. Somebody outside would basically create a copy or implementation, open source implementation of that. That usually just wasn't as good. But eventually, that would become popular. Lots of people would use it. Not great for them. And eventually, in fact, by then Google also had cloud, so it wasn't great for Google Cloud either. Here, we saw an opportunity to not just, because it's early days of deep learning, we knew it was starting to grow. There was an opportunity to sort of build something like a standard for this around a tool that we could help deliver. It would help from a research perspective, because we thought research would go faster. And over the years, we've definitely seen improvements because of these tools now. Two, we thought it is an important tool, and bringing a lot of this value to others outside Google is valuable as well. So that's great. This just the paper doesn't help enough. Having the code itself is going to make that a lot better too. And then finally, from a pure, if you think about Google perspective, how we can leverage it and improve things and deliver things on Google Cloud really helps Google as well, in addition to how it helps all the other products as well. So combining all these is how we sort of got to that. And with hindsight, of course, it was a great decision, and kudos to Jeff to think about that.
So TensorFlow has numerous exciting applications, like image recognition to time series to video detection and a lot more. What excites you the most regarding TensorFlow, and where do you think its application can be expanded?
So honestly, in more than a single application, what excites me a lot about TensorFlow is just the kind of reach it has. We're talking to students here, of course, at IIT, colleges, people who are studying this kind of stuff, but even seen high schoolers pick this up, sometimes even middle schoolers. And it's really amazing to see what students are doing today with these kind of tools, and how they're exploring new ideas and they're able to drive things. So that's sort of probably number one for me. Two, in terms of different kinds of applications and where we're pushing it, one area that I think, again, has a lot of impact, and we're seeing this today, is just healthcare, where we see a huge value of applying deep learning, and we are starting to see very early use cases. There's been a lot of research, but we are seeing on the ophthalmology side or diabetic retinopathy side, some work at Google that's, I believe, been deployed or being worked in parts of India. But more recently, even with COVID-19, a company in India called Cure.ai has done some great work in making it easier for detecting some of the chest, signs or symptoms from chest X-rays. So these kind of areas have really huge impact or change of how it impacts the world. The other parts, I guess it's great to see, the phone, even the phone that I have in my hand. There's a lot of stuff running on this, lots of machine learning, both in what's used in the cloud, but also what runs on the phone, all the way from just the camera that gets used, or just every little thing that runs there. And it's exciting to see all of that happening.
Your journey from IIT Delhi to organizations like Infosys, Morgan Stanley, Attributor, eBay, and then Google is quite inspiring. Tell us a bit more about your days at IIT and how you ended up at such big companies.
Uh, yeah, the my days at IIT were, I would say, a lot of fun, but I was a very different person back then in that I I did a lot of fun things, not as much studying, and some parts of that I regret. Other parts I don't, because I did learn a lot from my friends back then. Made a lot of really good friends who are still to this day really good, and we meet up and talk about things. The learning experiences from then on, really, I would say, it was. I think for me, like I was saying earlier, it was important to learn in every place, right? I cared about, in some ways, maybe I was catching up on all the learning that I hadn't done at IIT, I guess, afterwards. And so I often, in my early years, I did go from one company to another quite often, every year or two, because I didn't see the kind of things that I wanted to do. Or often I would go to a small company, a startup, where I would learn a lot in the early days. But then, unless that startup continues to grow, there's you start to get limited in where you can go. So that exploration did help me from the breadth of knowledge that I gathered over time, from the kind of people I worked with, and from the experiences I got early days in Bangalore, in fact, with Infosys and a few startups, and then here in Silicon Valley, going through the first downturn I saw, the dot-com boom or whatever, the crash in 2000s, and so all of these had different learning. Starting to see more often, I think, hope to see a lot more.
Right. So, what ideas are you currently working on right now, and how do you plan on implementing machine learning ideas in the business world? How do you think it will have an impact on the general public?
Yeah, so one of the limitations, so with over the last few years with TensorFlow and all the things that are happening in machine learning, there's this huge uptick in people trying these ideas out and exploring. And there are some specific areas where they've been successful. For example, image models. You can pick an off-the-shelf image model, whatever the device that's pre-trained, maybe apply it to one specific use case, and you'll probably be okay. And there's been, some very, very specific things that are working there. But if you go broadly, especially in businesses, there's a lot of data that's there in standard tables and so on. And it's still today, even with two tools like, I think this value is closer to what these business users are trying to do. So my goal, the place I'm looking at is still where there's lots of data for businesses, and how can businesses really understand that data better and do more with it. And so that's sort of the space I'm looking at, and I see a lot of opportunity for both from building a business perspective, but also for the businesses themselves and how far they can leverage it.
One more question related to AI. A major question when it comes to AI is machine ethics. How are we progressing in that direction? Because some fear that there might be an apocalyptic event in the future because of AI.
Yes, that's always there, and not to say that we should ignore that, but like I was saying about AGI, or artificial general intelligence, that still seems far away. Again, when it happens, it might happen pretty quickly, so it's good to be prepared. But that said, a lot more than that, I would say things that we should think about are areas that it's going to impact us now or in the near future. One of those is just job losses or changes in job. I mean, I wouldn't say job losses per se, but changes in the kind of jobs, because some of those jobs that we have today are going to be automated. And we're probably going to see some acceleration of that with the kind of situation we are in today, where we can't just go out and do every single thing that we used to. So the more automation does help, more of the stuff is moving to the electronic side and the digital side, and that sort of accelerates this. Now that those kind of job removals or replacements or automation will usually result in new kinds of jobs in a different area, but that is going to lead to major changes in what people are doing. And so somebody who's doing a job that's now automated, they need to be retooled. They need to think about how to do this again. And we need to help and think about how do we make the right kind of policies to help them with those. So areas like that are definitely something that we need to worry about. There are, in fact, some very more specific, technology specific things that we should also think about. With each of these advances, what you can do with this AI becomes more and more powerful. So one example is this idea of deep fakes that you may have heard of, where the idea is you can take a video and change the face, change the voice, and it looks very, very real, way better than what you would do in Photoshop, or even most big movies would do in the past days, right? So, and it can be done on basically any machine today, very, very easy manner. You can find this off the shelf. And things like that have the potential to spread misinformation in lots of ways. And it's important to be careful and mindful about how those get used. Be mindful about, where every new piece of technology that we're doing, what kind of, harm that it can cause. Not just the apocalyptic ones, but just these small ones. And then the humans are connected with each other in lots of ways, and one of those is the kind of conversations we have, or the kind of how we exchange ideas and stuff. And this technology has room to, in some ways, change and spread a lot more misinformation through the same kind of media in ways that it's very hard for most people to detect. So that's probably a much bigger area to worry about than in a future apocalypse.
So we've managed to collect a few questions from our audience as well. I'll ask them now.
Sure.
Given the expenses, how do you think we can make machine learning and deep learning tools accessible to the general public?
Yeah, I would say, the expenses used to be high. They've gotten a lot better. The hardware improvements are helping. Things like cloud are making it easier for most people to get access. Again, not free, but cheaper. In fact, in some cases, free as well. So, for example, if and I'm not 100% sure if Google Colab is accessible in India, but that's a great way to access a Jupyter notebook in the cloud, completely hosted for free, to do basic experiments and do a lot of things. So there are lots of opportunities for anyone to really pick things up and get started very cheaply and for free. And I would say, definitely explore those.
All right. Next question. Will federated learning be used in products in future to ensure data privacy?
Absolutely. I think that's a great direction to go towards. There are some products, for example, the keyboard that runs on Android phones today actually uses that already. So, stuff you type on the keyboard doesn't go in the cloud. It stays on your phone. And so federated learning is used to be able to learn across so many of those devices in a good way. It is still, I would say, it's not as easy to use as just learning in the cloud, so it's still taking longer to get there. But over time, I do expect more of this to move towards the devices.
What components are needed for a successful machine learning deployment, and what sort of infrastructure is needed to support it?
From a confidence perspective, it really depends on the application that you have. In some cases, for example, say the Google Photos case, right? You don't need to be perfect every time, as long as you're okay with not labeling every single thing that's in every single picture, you're fine. So also depends on how you build the product around that. Now, in another case, say a medical application, it's really important for you to be really, really accurate. In fact, if you go to something like self-driving cars, even 5 nines, you're not sure if that's enough. You probably want to go beyond it as far as you can go. So it really varies by application. From the infrastructure perspective, I again depends on the model size, depends on where you're deploying it, all of that good stuff. The good thing today is the tools make it easy for you to deploy, and the compute, etc., that's needed. You can run most models on this phone that I have in my hand. This is like a year and a half old phone. So most things can run pretty much everywhere, especially from a deployment perspective. Of course, if you need a lot more scale, then clouds are a great way to go for that.
Okay. How accurate is the current ML technology in predicting numbers in scenarios like the current COVID pandemic? Because earlier, Bill Gates had also predicted the outcome of a virus outbreak using computational models. So, how accurate is it?
Yeah, there's like so in something like COVID, there's a lot that goes on in terms of how you think about the model. It's not about just throwing a lot of numbers at it and expecting a model to give you the perfect predictions or whatever. There are a lot of assumptions that go into these models, partly because there's a lot of domain specific knowledge that we're leveraging, the people who understand these kind of things. You can use computers for simulations, and you're trying to mix really some predictions with simulations because you can leverage